course it is. Well, okay. Let's pretend everyone just remember this set and we'll look back in your notes and bring it up again. I think I'm even going to bring it up tomorrow, seeing at the speed at which we're going through it. But okay, so now that you guys have seen what's up with Q. So I'm not going to construct R, but I'm going to basically give you all the necessary words so we can understand R for what it really is. Not all of them, but a lot of them today. So let's just start from the very bare bones thing. And the thing is, Q is this special object called a field. So maybe we should define what a field is. This is where I get messed up. Let's start with more basic stuff. So basic definition. Now this is actually where the course is starting as far as I'm concerned. Before it was just sort of like a taste of what's yet to come. So here's a definition. So first maybe the empty set. Also known as this. I'm not actually going to define this. I'm just using this is more notation. I'm not a set theorist, so I don't want to get into it. This is the set with no elements, right? And this is the symbol for the set with no elements. I'm sure most of you have seen this. I just want you to know this. If I ever write this, this is a valid set. And oftentimes I'll say, so I'll often say let S be a non-empty set. It means a set that's not that set. Okay? And the reason I bring this up is because I'm going to say everything in the future. What else do I want to say? So I'm also not going to define a set. Do you guys have an idea what a set is? Think of it as a bag of junk. Don't worry about what makes a set because it turns out there's things that aren't sets. Like this. There's no settable set. Don't worry about that. The general idea is to think of it as a bag of junk. It can be an arbitrarily large bag of junk, but it has a certain size. That's what matters. What was I saying? Right. So let's say if A and B are sets, we say, so the words are A is contained in B, but I'm just gonna write this. It's contained in A. So realize I've written the other symbol. This annoys some graders. I actually don't know how to grade it well enough. There's this symbol, which is element of. It means P is something in, so something in the bag. Or this is like saying this is a smaller bag inside your big bag, right? Like maybe your coin purse inside your purse. I don't know. I'm bad at these real life examples. But this is just A is contained in B if. So the reason I'm putting this down is so now nobody has an excuse of not knowing how to prove a statement like this. If every x in B, so for all x in A, x is in B. This is the precise definition of it. So if every element of A is an element of B, we say A is contained in B. That kind of makes sense. And we say, so we say A is contained in B, or we might say, so this is A is contained in B, or A is a subset of B. So one thing I'm not exactly happy with this book about is it doesn't exactly specify if it means proper or not. But maybe it doesn't, I just didn't really care. But I'll check that out in a second moment. Okay, fine. So then the other word, you guys know what it means if I said A is a proper subset of B? So I'll give you that definition. It's a definition. Right, erase the stupid line. I'm sorry. Be continued. If A is a proper subset, if there exists something in B such that X is non-net. Or another way to say this is, okay. So I say something's a proper subset if it's not everything. Right, there's something missing. And that'll make, and I didn't notice I didn't say A equals B, or A does not equal B, because I actually haven't defined what that means, but that's the next thing I'm going to define. And the reason I'm just giving you these definitions is because if I ask you to prove something like, show that A is contained in B, you prove this statement. This is your want to show statement. You take something in A, and you show it's in B. Okay? So the last thing I want to say is, I would say A equals B if what? A is contained in B, and B is contained in A. And then, so that means if I show these two sets are equal, you do this double containment argument. And maybe I'll get a chance to show it, but not today, I think. I just want to give you these basic things. These come up a lot first. Let's hope I'm not going too slow. Okay, great. So now I can finally define something, kind of. I'm going to use that whole other word to define it. Right, so the word I want to define, this is my first somewhat significant definition that I'm only going to use today. I don't like wording for this reason, but it makes sense to do it because I'm going to use it for like a couple days, I suppose. A set F with two operations. And for the sake of just simplicity, we're always going to call these plus and times. Is called a field, and this is where I always mess everything up. So I'm going to give you a bunch of axioms, and I'm going to do it the same way Version does, even though I don't like this order, but whatever. So the first thing I ask, so there's a couple ways, I'm going to write this in two different ways, but one way of saying it is that plus is a function from F, okay, maybe I shouldn't do this. Well, I'll just say this anyway in case people like it this way. F cross F to F. That doesn't make a lot of sense. You'll see what I mean. Or the equivalent thing is if X and Y are in F, X plus Y is in F. This is the equivalent one. I just wanted to show you this because if you ever take other classes, some books feel like they have to be as pretentious as possible and they write stuff like this, which is really kind of a weird thing to write. But what it's just saying is you can think of the plus function that when you put A and B into plus, you get A plus B. And what this is saying is that if I'm given two things in F and I plug plus in, I get something else in F. Does that make sense? These are the same statement. I just wanted to show you this because I don't know. I found these nice lecture notes to help me like organize my thoughts, teaching how to read, and even they did this. And I'm like, why would you do that? It's just pretentious. But okay, fine. The point is just understand them. A2. What was the order? So this is addition is commutative. So maybe I'll just say for all x, y, z in F. I'm just going to put this at the top so I don't have to keep repeating myself. Yeah.
What does the cross mean? F.
Right. So that's why I didn't want to say it. That's why I was kind of debating. The cross just means two copies, as in like R2 can be thought of as R cross R. It's ordered pairs of something in R and something in R. F cross F is something in F and something in F. Does that make sense? That's all it is. It's overly fancy notation for a very simple idea. But it's very useful later. Like there's some really characters and other things you can do as well. So again, if x, y, and z are in there, but in this case x plus y, is equal to y plus x. Right? This is that addition is commutative. I don't know why he ordered it in this way. I would have put associative first, but it's also that addition is associative. If you add x and y and then you add z, it's the same as if you add x. Yeah, I'm not going to have enough space on this board, but whatever. I'm going to get all the axioms for addition down, then I'll deal with the other ones on another board. So then you also have, this is the commutative property. And this is the associative property. I actually don't, whatever. Right, I'm sure you guys have all heard of these, and I'm going to fit, yeah, I don't want to fit them all in one board. I'm just going to have to use all the boards to find stuff. Great. So we say, so A4, you guys are going to hate, there's a whole lot of these. There exists something in F, we're calling it 0, such that x plus 0 equals x. Now, by the way, that for all x, y, z, and f carries over for the definition. So x is something in F. So this is what we call the additive identity. I mean, technically, yeah. There's longer names for all these things. I just have 3 words, so I'm not saying everything right now. It's not so important. You guys should know these. And the last question is, what was the last one? Right. No, that's wrong. Right. So for all x in F, there exists minus x in F, such that x plus minus x is 0. So this is the additive inverses.